Thank you, Jousef, for the kind invitation. I will actually start to give just a little bit of background about my career so far and set the context for the rest of the lecture. So my background is on computer science and machine learning, and I consider myself a machine learning generalist. So I didn't specialize in a specific field of machine learning, but I touch many different aspects of it. So initially I did some time series forecasting and time series anomaly detections in places like Siemens and European Space Agency. I worked briefly on a startup with combinatorial optimization problems. I did research in computer vision, both in more academia like EPFL in Switzerland and a startup. Then I moved to London and I worked in search and ranking for a search engine, Bing, that is part of Microsoft. And then when I joined DeepMind, I worked both in reinforcement learning and computational biology. And now as a co-founder at Inductiva, which is a research-driven startup at the intersection of machine learning and science, I work in diverse problems in math, physics, and biology. So in this talk, I will share the lessons learned mostly from these two last experiences. So at DeepMind, I was one of the first members of the AlphaFold team. Actually, I can share a fun fact, which is it started with a hackathon. So my colleagues, Rich Even and Marek Barinsky and myself, we played around during 2 or 3 days with this Foldit game from the University of Washington and tried to hack some scripts in Lua at that time, which was the scripting language that interfaces with the game, to train some neural networks to make decisions on how to fold proteins. And it happened that people got so enthusiastic internally that it turned into a real project, and it ran for 4 or 5 years, and it had huge success. I think you heard already in this workshop a little bit about it, and I will also mention some of the learnings from it. And now, as a co-founder at Inductiva, we have a team of more than 10 people, almost 15, working in different problems on scientific machine learning. So I also gather more intuitions from this experience. So let's get started. I'll start by explaining a bit the title. So what do I mean by scientific problems, right? Not all scientific problems are easily tackled by machine learning, but I will give some examples. So in the field of biology, for example, the one I mentioned with AlphaFold, for example, it's a problem in which you are given a sequence of amino acids. So it's basically like a string, and you want to predict the structure of the protein. So it's like its atom coordinates or angles between residues. But you also have different problems that are actually very relevant for applications like drug design. So for example, given a biomolecule like a protein, how does this interact, and is there some binding with the ligand, some molecule that could be a potential drug candidate or some other biomolecule? So these are problems that are prediction tasks that you are able to specify and model computationally, and you have some hope to tackle with deep learning. In the field of chemistry, likewise, right? You can think of a wide range of molecules, and there are tasks like predicting their properties, boiling point, solubility, density, and so on, or not just properties of isolated molecules, but when they form like a material, right? So what are their properties in terms of electrical resistance, conductivity, etc. So these again are potential problems to be tackled with machine learning. In physics in general, well, pretty much all the subfields of, let's say, computational physics can be potentially tackled with machine learning, right? So once you have clear inputs and outputs, typically you want to simulate the behavior of a system, either in fluid dynamics or perhaps structural mechanics, or even again at a very small level where you have quantum mechanics that describes the state of matter at the level of atoms and electrons, potentially you could tackle this with machine learning, for example, finding the wave functions for some atoms. And even in mathematics, we have seen recent uses of deep learning that are very promising, right? So I mentioned here also some work from DeepMind on combinatorial optimization problems, for example, in which you attempt to have algorithms that make use of neural networks to make more efficient search of a very big search space. You have also a recent example of algorithmic improvement. So for example, just 1 week or 2 weeks ago, DeepMind published this paper on improving the performance of a matrix multiplication algorithm. So how to use reinforcement learning to learn a sequence of instructions you need to perform to have the matrix multiplication calculated, but using fewer operations such as additions and multiplications. And we have even seen examples of using deep learning to help in theorem proving. So this can be seen also as a way of searching in a big combinatorial space of, when you start with axioms and you want to prove theorems, and you have a set of logical rules that hold, proving a theorem is kind of finding a path from axioms to that complicated theorem in a huge space of combinations. And we have seen also from a paper from DeepMind on knot theory that of a blend between humans and computers in which the computer is giving some partial intuition on where to look for theorems, and then the humans are actually making the proofs. But this was just to give you a notion of the wide range of problems in different fundamental sciences that have now started to be tackled by deep learning. And this, you cannot forget that it has a lot of impact, not just in theory, in fundamental sciences, but in many, trillion-dollar industries, right? You can think of energy, material design, drug design from pharma, aerospace, telecommunications, or construction, or even IT hardware. So all of these percolates naturally from the progress in the natural sciences. So what I want to do now, in 2 slides, is just clarify what I mean by deep learning, and I cannot give you in such a short amount of time the background. But it's basically a rebranding of the study of neural networks, and the name deep came from the fact that now we are able to train neural networks with several layers. Typically, when people like 15 years or so ago were somewhat limited to train neural networks with 1, 2 layers, that would be called a shallow architecture, right? So the fact of having multiple layers brought the name deep into the learning. And as usual in neural networks, you can think of them as general parametric function approximators. So you'll have a set of free parameters you want to approximate some function, and this is a tool that allows you to do that in a generic way. It will benefit from being fully differentiable by backpropagation, which means finding optimal parameters, which is the process of training, of learning, can be done by gradient descent algorithms, right? So this is basically what I mean by deep learning. And as you know, and you probably heard many times, there are a few ingredients for the recent success since basically around 2010. Which many of them were related to scale. So lots of free parameters. So you have more layers and with bigger matrices, let's say. We started to see the availability of a lot more data, a lot more computational resources, coupled with a few algorithmic tricks that made learning more stable. And all of this progressively led to the availability of much better software libraries for deep learning, the famous ones like TensorFlow, PyTorch, and recently JAX. So what we'll be talking here from now on, it's now that you have the context of the kind of scientific problems that I believe it can be tackled by deep learning. This talk will focus on some of the lessons learned and best practices that I observed through my experience. And this should give you a good notion if you are embarking in such a project on, you know, what are things that worked in successful projects. So the first aspect of it is that you need to translate your science problem into a machine learning formulation. So this sounds easier, it's easier said than done, right? So it's not actually very obvious and non-trivial, because your choice of what exactly are the inputs and the outputs can evolve quite a lot. And it depends on the data regime you are. So for example, if you have a lot of data and you know exactly what you want to predict and from what inputs, you know, the translation, it's relatively straightforward. However, if you train your first model in that regime and you notice that you don't have enough data, you immediately overfit, you might be forced to reformulate the problem. So now you might be forced to predict something that is easier, or for which it's easier to regularize, or for which it's easier to add more data, more sources of data. And you might be going back and forth in this process of what is my machine learning task? What am I trying to predict? Many times, what is my loss function? So this is like, it's an iterative process, and you'll be doing this many times. So it's not as easy as it sounded. Okay, this is the problem I want to solve. This is the formulation. Obviously, you can use some templates, some guidelines from other communities that are not applying deep learning to science, but applying to computer vision, natural language, and so on. But you know, be aware that science is a little bit different, so you can reuse only so much. The second thing you should really strive for is to take the most out of deep learning, is to do end-to-end learning, right? So traditionally, machine learning had this pipeline of, you know, you have some input, you have some feature extraction that could be capturing some human intuition about the domain, and then you have the machine learning model, right? But the disruption that deep learning caused in many fields like computer vision, speech, natural language, and so on, was to actually train deep neural networks that operate directly on the raw inputs and that predicted the quantity of interest directly, and everything is learned end to end. Again, this is easier said than done. So for example, I will actually give here an example of AlphaFold. I worked only on AlphaFold 1, not in 2, but in AlphaFold 1, obviously we knew by being at DeepMind that we want to have an end-to-end learning system, but it was not that easy, because if the first attempt you do, like predict the protein structure from the sequence, revealed not to give enough data, and the predictions didn't generalize well, and it was really tricky. So after a lot of iteration, the best we come up to in AlphaFold 1 was actually a two-stage system in which initially you would predict pairwise distances between amino acids, or actually a distribution of their distance like an histogram. Eventually, perhaps coupled with some predictions about their angles as well. And this would encode basically a scoring function that would be applied to the current configuration of the protein. So given like some random configuration of the protein, you would ask, am I respecting the predictions on the distances between pairwise of amino acids? Am I respecting the predictions on the angle distances? And this gives you a scoring function. But now, in order to find the structure that solves that is the best one, that with the best score, you need to solve an optimization problem. And this you could do with some optimizers, sort of gradient descent-like. And this revealed to be good enough to win the CASP 13 competition, which is a worldwide evaluation of many computational biology laboratories around the world. And AlphaFold won first place with a relatively, well, not such a huge margin, but a decent margin compared to the second, even though it was not fully end-to-end learning system. It had two stages. The only part that was end-to-end learning was predicting the pairwise distances, but then it had the optimizer at the end. In AlphaFold 2, my colleagues, they managed to go further, right? So now it's really an end-to-end learning system, a much more complicated neural network architecture with more layers and so on, in which perhaps one way to interpret it is in the first layers, you still do this kind of predictions on pairwise distances, and you incorporate some other additional information from genetic database or templates. And then it's as if the upper layers were kind of doing the search in a differentiable manner, right? Like they kind of can have many layers of neural network, many layers, and there is this even recycling, there is cycle that you could almost interpret it as this being a differentiable search. So now this can be trained end to end, and obviously, as you know, AlphaFold 2 was even more successful to the point that the problem of protein structure prediction was considered nearly solved by the community. And I would argue that great part of the reason was that finally DeepMind managed to do this fully end-to-end learning on AlphaFold. So, like I said, easier said than done. Another important learning is that priors matter a lot, right? So I think you've seen perhaps even today a talk about geometric deep learning. So you have heard about the concepts of invariances and equivariances. What this means is that some a neural network layer, let's talk at the level of layers, for example, will be, let's say, invariant to a transformation, let's say, of scaling. For example, here we see the cat. If by scaling the input, your output is the same, so it's invariant, it doesn't change. And it would be equivariant if by applying that same transformation, your output would be transformed in the same way. So in this case of image segmentation, that would be segmentation of a cat. Well, now the learning here is that this is much better than doing data augmentation. So the alternative would be, okay, my neural network architecture is not built in to be invariant to these operations or equivariant. And I will have to learn that by providing a lot of modified examples in which I introduce perturbations on the input, like scaling, translations, and rotations. So obviously, by doing this, if you would do the data augmentation way, your learning would not be guaranteed. So you could have a neural network in which the property would not necessarily hold, and you would need a lot more data. So it would also be harder to train. So this is another learning that in many domains, okay, if you can incorporate priors that you know that are hold true, just do it, right? Another learning that people have realized in many tasks is, try to predict everything, many things. So multitask learning, right? It's one of the best regularizers. So suppose you are trying to use a neural network to predict the simulation of, I don't know, some fluid dynamics scenario. And actually the metric, the thing you care about is just one small scalar at the end, I don't know, counting how much water dropped overtopped over that wall or something like that. If you train a neural network to predict just that scalar, you would incur a lot more risk of overfitting, right? Because your input is maybe high dimensionality, you are representing the input of the problem, the scene, and so on, and the initial conditions, and you are just predicting one scalar. So if you have not that much, if you have even tens of thousands of simulations, and you are still just predicting a scalar, it would be really easy to overfit and just memorize to distinguish different inputs and predict this scalar. However, if you force your neural network to predict like everything you can simulate, like, I don't know, at every time step, predict all the vector velocities of all the fields, vector fields and accelerations in every point and so on, this would be one of the best possible regularizers for your neural network, because the inner layers that have a latent representation that captures the physics, it's forced to be so good that it's able to predict all of these quantities. So there is no longer a way to cheat and just predict a small scalar at the end that is relevant. It really needs to learn a representation that is so meaningful that you can predict all of these quantities. Even if the one you care about is just one, predict everything. Obviously, then there is the effect of scale. So scale is important. With this image from a cluster of TPUs at Google, I'm not trying to claim that you need to be Google to tackle scientific problems with deep learning. At the moment, I mean, at Inductiva, we're a small startup and we don't have these resources. And it's not because of that we are afraid of tackling them. I'm just saying that to some extent, scale does matter, and it matters for different things. So it matters for training larger models and training them faster. And it matters for trying different architectures or hyperparameter tuning. So in one case, it's like, okay, you want to speed up the training of just one model, right? You want to get results faster and eventually train models with higher capacity to fit your data. And in the other case, you want to launch a lot of training processes in parallel to find the best architectures. So again, I don't think you need to be Google for this, but definitely having a good GPU win, it's a clear win. I mean, you can easily see speedups of factor of 50 over a modern CPU. So, and training with multiple GPUs will help. So to get to the level of having decent sized models, computational infrastructure scale matters. The same can be said in terms of scale of data, right? Obviously, the easiest way to overfit and not generalize well is just to have a small data set. And in the case, for example, I have here on the left, this is the protein data bank, was kind of the source of protein ground truth, like that was experimentally collected throughout the years, like maybe decades, by the research community. And if this was not available, AlphaFold would not be possible, right? And even with the whole community contributing to this was on the order of some tens of thousands of examples of proteins, which might still be tricky for deep learning. It might still be a low data regime. That's why it was not trivial to just train and get the best results, right? For example, in computer vision tasks, you often have access to millions or tens of millions of images, which in a science problem, if it depends on experimental data collection in the lab, it might be harder to get. But definitely it's a component that will obviously help. And I have a third slide here regarding scale, just as a reminder. Actually, this plot is about the reinforcement learning setup. But just to give you an idea, on the fact that learning might take off sometimes quite late. So if you see on the x-axis, these are millions of frames. So interactions with that the agent does with, this is a set of games. And so it's millions of frames. So if your computational resources would be, okay, I'm able to train for, let's say, 1 million frames, which looks quite a lot. your performance would be down there in the corner of being super far from human performance. Whereas actually with the exact same algorithm and exactly same setup, if you can afford to train for 40 million steps or 100 million steps, the performance keeps improving. So this is, again, I don't want to say that only the biggest corporations can afford to do this. I'm just saying that it's interesting to see that exactly the same algorithm, exactly the same setup can lead to very different conclusions depending on the scale at you are executing it, right? So if you just zoom in on the corner, you would think that this is not really working. And actually it does if you can afford to train for longer. Okay, so now I have here one message which is perhaps a little bit harder to communicate, to come across, but which is search, or maybe you think of computation distills into learning. So what do I mean by this? Perhaps one analogy that is this image that illustrates, for example, AlphaGo, or in a game where you have a big search tree. It can be a game or any other thing where you have a big search tree. You can always search the tree with some not very clever rule, and you can be very fast. And so by trying a lot of possibilities, visiting a lot of nodes and so on, you are doing compute, right? You're searching. It can be a very exhaustive search. What we have learned from AlphaGo and other systems is that this search can be distilled into knowledge. So what do I mean? By having done all that effort of visiting nodes and collecting statistics, you can now use this data to train neural networks that will make the prediction of how promising it is to follow this search branch. Should I go there or should I go the other way? So this is why DREAMT is interesting, right? Because it's kind of an equivalence between search and learning, and you can distill one into the other. Likewise, in AlphaFold, in AlphaFold 2, you also have a process of distillation in which, by having an initial predictor, a neural network that does already quite well, you can evaluate, you can make predictions on much bigger data sets than the ones you have available for training. And if you have a way to just keep the ones you have high confidence on, you can feed those back into learning and extend your data set. It's kind of a distillation, kind of bootstrapping your learning by doing more computation, prediction, and then learning from it. Likewise, if you are dealing with physics simulator, so it's not really a search tree of a game or so, but you are predicting the evolution of, let's say, a fluid step by step, and you can do this many times. Again, you can distill this knowledge into a neural network that will learn to predict not just one step ahead, but maybe 10 steps ahead or 100 steps ahead, or even more, right? So it's interesting to keep in mind this trade-off. Okay, if I can throw a lot of compute to it, I can later distill it into knowledge that no longer needs to be so brute force. Okay, so now I will move on to some lessons learned that are more related to team organization aspects. So one, obviously, if you're tackling science domains, is try to have an interdisciplinary team. So this would be a mix of scientists, ideally that are experts in the domain you're trying to tackle, and machine learning engineers and researchers. But here I want to highlight something very important. You need to remember that you started by translating the problem into machine learning domain, and that's where you where you will execute. So actually the bottleneck, it's always how well can you execute in the machine learning domain. So you should have a lot more fluency in the machine learning part, and more of your team should be machine learning engineers than specialists from the domain. Actually, in AlphaFold 1, we started by being only machine learning engineers, and the only input we had from experts in computational biology was visit once every 2 weeks from a professor in computational biology that would give us some hints. So keep in mind that what people will be doing day to day is writing code to train neural networks, running experiments, collecting metrics, and so on. And the intuition from the science experts, it's important in the beginning to formulate the problem and occasionally to have some, clever idea on how to tackle it in a creative way that will help learning, maybe introducing those architectures that have some invariance that it holds. But keep the balance, knowing that the heavy lifting is more on the machine learning side. Another very, very clear learning is that from the beginning, you should have clear metrics. So there's this famous quote actually from the management domain as well, not for organizations, not only for science problems, that you can't improve what you don't measure. So, for example, again, in AlphaFold, it was very clear that we look at the metric from the competition that happens every 2 years, it's GDT score. It's a score between 0 and 100, 100 being a perfect prediction. And immediately from the beginning, okay, let's make sure we can evaluate our models using this metric. We have a test set that makes sense. It replicates also the conditions of the competition. And now this is our north. So this is super important for a team, right? To know where do you stand. Once you have this, you can go a bit further, which is have a leaderboard. So now I have some screenshots from Kaggle. Kaggle is famous for machine learning as a site that holds machine learning competitions. You can do this internally, sort of, right? Let's put it this way. If you have many people independently trying to tackle the same problem, you could have a leaderboard that ranks their individual contributions or their specific algorithm. But normally, actually, you have a team working together. So what you want in the leaderboard is not so much who is ahead and so on. It's like a team effort. It's more something like below. It's like, how are you progressing through time, right? Like, okay, what was my metric, last week and 2 weeks ago and 6 months ago, and where do I stand now? It's more to track progress and see how fast you're going. Is it are you stuck there in a plateau, or it's kind of taking off? What were the contributions and what time did they happen, and which ones had the biggest impact? And this is very encouraging also for the team, right? If you are able to see incremental progress happening every week, you are on track, right? And again, in AlphaFold, it was actually a relatively slow process. Every week, you would increase a little bit the score, but by 1% or to be very. It was kind of a linear progression, nothing like an exponential takeoff or anything. Nothing magic happened. It was very gradual. So once you have that, right, you have clear metrics, you have perhaps even a leaderboard. You have to ask yourself, right, how fast can you iterate? This boils down to how many ideas you can test in in the next 6 months. And this will basically determine pretty much your success, right? Because if you are in a team where you can in 6 months, test 30, 40 or 50 different ideas, you'll probably do pretty well, right? If it takes you 6 months to test 2 or 3 ideas, you need to be very lucky, right? And again, I keep coming back to the example of AlphaFold. If you look even at AlphaFold 2, there's a series in the Nature paper of 7 or 8 contributions that all helped move the score a little bit. And in the ablation study, you can turn them on and off. And, it's just small improvements when you turn them on, and there's not one that dominates. And so you can imagine, to get to that set of 7, 8 things that made a difference and all had to be combined, how many more good ideas had to be tested, did not work. So if you cannot iterate fast enough on this kind of A/B test, right, like these randomized controlled trials of ideas and testing new models and new tricks, it's going to be very hard. One way to make this happen, right, to help accelerate the experimentation cycle, is obviously having good tools. And here, I mean, luckily, you no longer need to be, again, in a big tech company. There are amazing open source libraries that are widely available, right? Pretty much everyone uses either TensorFlow, PyTorch, or JAX. And for things like doing distributed deep learning, there are amazing things like Ray now that can really scale your experiments, and you can use any public cloud or your local cluster, and it's really neat. And obviously there are now many tools for experiment tracking as well, which you will, like MLflow, in which you will keep track of which experiments you launched, which hyperparameters you had, what were the outcomes of these, which metrics you got, and so on. So this used to be, you know, if you'd be doing, I was doing machine learning like 15 years ago, this was really frustrating, right? Because you didn't have very good machine learning libraries. You had to write a lot of things from scratch. I wrote machine learning algorithms from scratch in C, right? You had no easy way to distribute compute using cloud and with very little code overhead. And you had no tools for experiment tracking. So this is like a golden age of deep learning experimentation in which anyone can have pretty much state-of-the-art software to do machine learning research. And this is not a bottleneck, no. So actually, you might have noticed that many of the things I said so far are not super specific for science problems, right? It could be applied to many deep learning problems in other domains, right? So in the remaining slides, I will just highlight what I believe are some of the differences of tackling science problems, in addition to all these best practices we heard that apply to science, but many of them are also applicable to other domains. So one important thing to notice is that your data now comes from physical processes, not like human behaviors. And, you know, physical laws that describe physical systems are not that many. They are represented by equations. Often they are deterministic. In some cases, they might be stochastic, or they might have some chaotic rules, but in many cases, they are pretty deterministic. And, you know, they might be hard to compute and so on, but okay, it's there, right? Compare this to domains in which machine learning is operated that are, I think, much more messy and arbitrary, like human language. Different kinds of language, right? It's a lot more arbitrary. And some problems in human perception, right? Even in vision and understanding of scenes and other aspects, or perhaps even, I don't know, perhaps even speech. These, I would argue, are more messy domains. So the fact that you are operating in a scientific domain, that you have data that describes a physical process, or perhaps you are even in mathematics, in which things it will be even neater, right? You have pretty much no problem of noise, compact description of the problem. It's just hard computational, but everything is neat. This is, I think, one very interesting thing from working in science problems. And again, you can actually know the physical laws are pretty much known for all the domains of interest that have like real world applications, right? We're not perhaps talking about string theory and, you know, quantum field theory and like unifying laws. We are normally dealing with systems at the scale that are already well understood. So coming back to things that I said in the beginning and you heard from other lectures in this workshop, there are ways to incorporate these physical laws as priors. So one of them will be kind of a soft prior that will be part of the loss function. And this could be the example of PINs, of physics-inspired neural networks, right? So if you have a partial differential equation, you will incorporate it as a term in your loss function. And this is a way to say, okay, I have this prior, which is this physical law that should hold, and I want my network to respect it. But it's not part of the neural network architecture, and it's not the case that it always holds true, but you put it in loss function, so you're trying to gradually enforce it. But I would call it a soft prior, because you have no guarantees that it will always be respected. And you have the hard priors, which are more built into the neural network architecture, and it connects to also what you heard earlier today on geometric deep learning. For example, if you would be doing graph neural networks to deal with molecules, and you have a representation of the atoms and how they are connected either by bonds or the nearby atoms, okay, you know that this neural network should be invariant, I don't know, to the rotation of the molecule, this should not matter, or the translation of the molecule, or the way you represent each node, the way the order by which you list it should not matter. So a permutation of the nodes should not matter. So if you know these kind of priors and you are able to incorporate them directly into the architecture, this I would call a hard prior, because by construction is always respected, you should do it. And what I'm claiming here is that by working in science domains, this might be easier to do than in other domains, right? Like if I'm modeling, let's say, a recommender system for a company, a web company, I will not have a partial differential equation that describes the behavior of humans, and that needs to be respected, right? So it's a lot messier. In addition to that, if you are in one of these physical domains, you can often simulate it, right? So what does this mean? This means that in principle, if you have access to a simulator, there are many open source, you could generate virtually unlimited amounts of high quality data if you can rely on this numerical simulation. So again, you would be in a regime that you don't suffer from data scarcity, unlike some other cases in, I don't know, maybe recommender systems or other things in which you cannot just simulate it, right? Or it's much harder. You really have to collect it from the real world or have humans annotate it. And maybe you'll have noisy labels and so on. So here you might be in a domain in which this is just not a problem. You can just generate a lot more data. You might have a problem in terms of what is called the sim to real gap, which means you are able to generate synthetic data, but there is a little bit of difference to what you would get with real data. And so if this affects the performance of your system, you need to be aware of it. For example, in robotics, it's quite a common scenario. You have simulators of robotic arms that can manipulate objects and so on. But once, for example, if you train a control policy using, let's say, reinforcement learning in such a simulator, and then you deploy it on a real robotic arm, it might underperform because it's not quite right. Maybe the friction in the joints or some other physical parameters are a bit different, and your policy no longer works. So this would be a problem of sim to real gap. And there's a whole set of techniques in deep learning to deal with this, right? In any case, it's still a privileged position to be, because you still can generate a lot of synthetic data, and then you need to be careful to to make the transition to real data and overcome this gap. But it's still a privileged position to be, in which, if, for example, if you are, again, trying to do a recommender system for, I don't know, ranking YouTube videos and suggestions or suggesting products in an e-commerce website, it's very hard to write a simulator of human behavior in which would capture really the behavior of people. It's really hard. You normally attempts to do that are very unfruitful, or you can, I mean, there's research trying to do that, but it's very hard to simulate what is the behavior, you know, of population of humans when they are shown recommendations. Very hard, right? I think another difference in terms of tackling science problems and not other different problems where machine learning has been applied is that the research community tends to be pretty open, right? So most data is publicly available. Like I mentioned in the beginning, AlphaFold was possible due to the Protein Data Bank, which was a community effort for decades. Whereas if you would, again, be doing research on a recommender system, this would be proprietary data from that service, right? Whether you are in, I don't know, Twitter, or Facebook, or Amazon, or so on. The data is held by the platform that controls this service. And by data protection, you know, even laws and privacy issues, they will not share this, right? So it will always be very hard to do research in these fields unless you are inside that company, and then what you do, it's on the proprietary data, but it does not necessarily translate well into other setups. So again, I think an advantage. Yes.
Sorry, just I've been paying attention, but in the details as much as I can. But just to bubble up one. What is a scientific problem anyway? Is it, you sounded like you rooted it in something that starts with laws of physics, and that it's you know, it's less messy than some of these other problems like human language and perception. Is there another way for you to describe a scientific problem? Because now if it's
so I started this talk by giving some examples in different domains like biology, chemistry, physics, and so on. But for example, yesterday there was this talk by Ben Musley, which he actually formulated this dichotomy pretty well, which in 3 categories actually on science problem, which was one was the forward simulation, right? You have the specification of the system and you want to simulate it. The other category was inverse problems, in which you just have the measurements and you want to infer the state that is hidden. And another category he mentioned was the inference of physical law. So you want to derive equations from it, right? I mean, all of these could be called science problems. In my talk, I'm focusing more probably on the first case, which is more related to simulation of systems. And when I say physical, it's in a broad sense. It could be at the level of chemistry or the level of biology. It's just different scales, right? But they are physical processes in the sense that even biology needs to respect the laws of physics, right? Yeah, does that answer your question?
Yeah.
Okay. But yeah, I agree that maybe you could have different formulations in some cases. You know, I don't know, in biology, you have a more kind of data science problems in which you have some data set, you need to fit make some prediction, and you don't have such a strong connection to the first principles that govern the phenomena. And maybe you would still call this a science problem, but here I'm focusing more on the ones in which you also have a first principles understanding of them to the level that you can either have equations or simulators as well, or it's math and you also have a full specification. So I'm focusing more on that subset.
Okay, yeah, that makes sense to me now. Yeah.
Okay, thank you. Yeah, and so as you might have understood already from these examples, there's a great variety of problems. There's, I believe, space for everyone. You can conduct a lot of research and feel that there's still many open problems. And last but not the least, I think the potential impact is huge. So one nice way of thinking about it is that when you solve problems or you innovate at this science level, this is like the roots of human knowledge. And then other things build on top of it, like engineering and many industrial applications. So this just percolates up, right? Like you saw examples also in this workshop. If you use, let's say, neural networks to find better solvers for partial differential equations, this will be used in many industries from, automotive to construction to anything, right? Or if you have impact on understanding molecules, this will be used for pharma and healthcare. So huge applications. One actually extreme example of this that I like to think of is also this work by DeepMind in collaboration with EPFL, in which they trained a neural network with reinforcement learning to control the magnetic field of tokamak, like this nuclear fusion reactor, to make sure it was more stable. So think of this: humanity is facing some problems, like lack of clean energy. That part of it, or the solution to it, part of it might come from the ability to be able to simulate well and have machine learning models that help in some core tasks like controlling the magnetic field of that reactor. So if you think that you can use deep learning to contribute to problems such as providing unlimited clean energy for humanity, this gives you an idea of the level of impact that you can have, right? Or if you think of understanding biology at the molecular level, and you think the impacts it has to cure disease and so on, this is really like the level at which we are talking, right? Many of the things you can do, or the breakthroughs that will come on using deep learning in science domains, are really the leaps we need as humanity. So I find this very exciting. So this is the end of my talk. I just have here a recap of the points I mentioned above. So just in 1 minute, I mean, if you are able to translate your problem well into machine learning, do end-to-end learning, you are able to incorporate priors, predict many things, and have enough scale, eventually enough scale even to distill lots of computation into more knowledge. And if at the team level, you have an interdisciplinary team, you have clear metrics, you are tracking your progress in a sort of a leaderboard, you have good enough tools to optimize your experimentation agility, you are in good shape to tackle one of these big challenge problems, right? And as I said, this field I think is particularly interesting because of how close you can be to having a first principles understanding of the phenomena. Sometimes you know the laws, sometimes you can simulate it. It's just that the complexity of the systems is big, right? You know how to, let's say, simulate one step. Like maybe the physical law tells you how to go one step ahead. But then you need to simulate at bigger scales. And that's where machine learning can come, right? It's like how to learn to go from first principles that are well understood to make predictions about things that are very complex. So this interplay between, you have good priors, you are able to simulate, and you are able to distill what you simulate into learning, I think it's of incredible potential. So that's what I wanted to share with you today. So if you have any questions, I'm happy to answer.
Great talk, Hugo. Really appreciate it. Any questions before we wrap it up, to Hugo. I mean, we should also say, do you have any resources that you could send us? Maybe interesting articles, maybe the website of you. The blog is very interesting.
Yes, I'll be happy to send you, Jousef, some links. Yes.
Perfect. And also the slides would be very great, so I can share them with the community as well.
Yes. So just out of curiosity, if I can ask a question to the audience, what field of science or engineering you are more familiar with, or you are working on, just to have an idea?
Maybe write it in the chat if you want. I think it's a mix of CFD. Okay, chemistry. We have chemistry from Simon.
Okay.
CFD, yes. What else? I think for me personally, it would probably be the intersection between engineering data, which is not common. So not time series data, maybe geometric data, and use machine learning for that to solve a specific problem. An example would be, for example, you have a sloshing. So sloshing in a tank, and you would try to find an optimal geometry based on that sloshing noise or airborne noise behavior.
Yes. So that's definitely one field we are very interested at Inductiva, which is how can you accelerate the physical simulations with machine learning to the point that then if you want to search a big design space where you can control where you place, you have some parameters that determine your design, you are able then to find a optimal solution or near optimal solution, right? So we are very interested in those kind of problems. So that's very nice.
Great. We also have other answers come mechanical engineering, structural dynamics, as well as CAD.
Yes, we have a collaboration with two PhD students in mechanical engineering. I think they will also be speakers in your workshop, where they try to solve this kind of problems of how structures deform, right, when you apply some forces. And again, this falls into the setup of where you need to solve some partial differential equation, which will be maybe some linear elasticity or other thing, and you have some geometry that describes the component, and you have some initial or boundary conditions. But as you have seen from previous talks, you can now approach this using pins or other machine learning based methods. So we are very interested in those things and how they then loop into this optimal design, how they connect to this optimal design loop in which not only you need to do one simulation, but many, right? So I think this is a recurrent problem that has many applications.
Very interesting. I think I have a ton more questions which I would like to ask you, but I keep them for the podcast. So I'll probably invite you around December-ish, if you have the time, and then I'll interview you on those questions. If there's no more questions, guys, I think we can wrap it up. Really great talk, Hugo. I learned a lot again. So that actually shows me how much I don't know, which is also good. Yeah. All right. If there are no more questions, Hugo, thank you so much again.
Fantastic. Thanks for having me here. Okay.
Bye-bye.
See you. Bye.